Hi students, today we will be talking about lipids. This is the last topic for the prelim period. For the information of everyone, the prelim exam is scheduled on the 24th and 25th of this month. We will just discuss in our group chat how we will conduct our exam. Now, basing on our conversation in the group chat, I guess there are no questions regarding cells and carbohydrates. I really hope that you all read the modules given and watched the videos. Be informed that topics there are presented simply so that it is easy for you to understand, even if we don't see each other and then discuss inside the classroom. Okay, so let's get started. Like organic molecules, biological molecules are grouped into families. There are four major families of biological molecules, including proteins, nucleic acids, carbohydrates, which we just had discussed, and of course this one, the lipids. The lipids are the subject of this unit. Of these four families, the lipids are structurally the most diverse. This is because, unlike members of the other three families, members of this family do not share a common structural feature, but rather they share a common physical property, and that is lipids are hydrophobic. So from the word hydrophobic, no? So these are two words joined together. So hydro means water, phobic from phobia, so fear. So lipids are water fearing, so they do not like water. Okay, so the chapter objectives of this lesson are: one is to distinguish between the different kinds of lipids, and the second one is to identify several major functions of lipids. Okay, so what are lipids? So how do we define lipids? Okay, so a lipid is defined as a biomolecule that contains fatty acid or a steroid nucleus. Okay, so these are examples of fatty acids: arachidic, stearic, palmitic. These are straight chain fatty acids. Okay, so makita ninyo na straight siya. And then on your right are bent fatty acids na bawg nga fatty acid, no? Bend or bent molecules. So oleic, arachidonic, and so on. Okay, you will know later nganong nakabawg sila. Okay, now an example of or a molecule of steroid. Okay, so this is a steroid nucleus. If you notice, as you can see, steroid nucleus has tetracyclic skeleton. Okay, so tetracyclic meaning four rings. So this tetracyclic skeleton consists of three fused six-membered ring. Okay, so you have the ABC and one five-membered ring, and that's D. And then if you count the number of carbons in a steroid nucleus, there are 17 carbons. Okay. A very important steroid, example of a steroid is cholesterol. So this is how cholesterol looks like. Okay, so cholesterol is a steroid. Okay. A steroid is soluble in organic solvents but not in water. So I described lipids in the first slide as hydrophobic. So they are water-fearing, they are water-insoluble biomolecules which have high solubility in nonpolar organic solvents such as chloroform. So lipids include a diverse group of compounds that are largely nonpolar in nature. As you can see, the steroid or the cholesterol is very nonpolar. It is tetracyclic, so it only has CH2 skeleton, so they are nonpolar. Now, They are hydrocarbons that include mostly nonpolar carbon-carbon or carbon-hydrogen bonds. And you know that nonpolar molecules are hydrophobic or insoluble in water. Okay, the term lipid, the word lipid comes from a Greek word lipos, which means fats. Okay, so they are extracted from cells using organic solvents because, as I've said, they only dissolve in nonpolar solvents. Okay. Polar solvents such as methanol are used to separate lipids from proteins, whereas nonpolar solvents such as chloroform are used to dissolve lipids. So lipids are usually extracted at low temperatures, as low as 4 degrees Celsius, as soon as possible after animal tissues are removed. Now, let's move on to the types of lipids. The first one are the waxes. Waxes are simple lipids which are esters of long-chain alcohol. These alcohols are usually monohydroxy that is with only one OH and with fatty acid. So an alcohol with a fatty acid. Now, the alcohol may contain from 12 to 32 carbon atoms. Waxes are found in nature as coatings on leaves and stems. This wax prevents the plants from losing excessive amounts of water. The leaves and fruits of many plants have many waxes coatings, which may protect them from dehydration and small predators. So if you wash your fruits and vegetables, if you notice, if you drop water on it, the water just drips on the outer covering of the fruits or vegetable. That is because these fruits and vegetables are coated with waxes. Now, the feathers of birds and the fur of some animals have similar coatings which serve as a water repellent. Now, the next one are the fats and oils, which are also called triacyl glycerols or TAGs, TAG, or they are also called triglycerides. Fats and oils are composed of 95% of fat in the foods we eat. Just imagine, 95% of the fats in the food are present in the food. Now, fats and oils are the most abundant lipids in nature. The fats and oils, or the triacyl glycerols, or the triglycerides, are also the main fat we store in our body. So, when you pinch an inch around your waist, you are pinching triglycerides. Okay, so if you have the belly button or belly, yes, then that is the adipose tissue made of fats and oils. But of course, there are also fats also functions as energy they provide energy for living organisms. They insulate body organs. That's why we don't feel cold right away. And they transport fat-soluble vitamins through the blood. So the vitamins A, D, E, K, which are fat-soluble vitamins. Okay, then let's go on to glycerophospholipids, or also known just simply as phospholipids. Glycerophospholipids or phospholipids are key molecules that contribute to the structural definition of cells and that participate in the regulation of many cellular processes. They are found in the highest amounts in the membranes of all cells and are present in very small quantities in fat stores. Then we have the prostaglandins. The prostaglandins are a group of lipids made at sites of tissue damage or infection that are involved in dealing with injury and illness. So if you feel pain, kay nasamad mo, or you have fever, then ang responsible ana nga lipid is the prostaglandin. Okay, so prostaglandins control processes such as inflammation, blood flow, the formation of blood clots, and the induction of labor. So kung kanang manganak na gani nga pertinang sakita, okay, so prostaglandins are synthesized or are present. Okay. Okay, then we have the steroids or the sterols. They are the least common type of lipids. They are found in tissues of animals. So cholesterol is perhaps the best well-known sterol. Though cholesterol has a notorious reputation, the body gets only a small amount of its cholesterol through food because nagaproduce jud pud ta og cholesterol. Our body normally or in nature produces cholesterol. Okay, cholesterol is an important component of the cell membrane and is required for the synthesis of sex hormones, vitamin D, and the bile salts. Okay, so these are the structures of lipids. Okay, so you have the fatty acids with the COOH. Then under this are the prostaglandins. Then we have the different types of lipids like waxes. Waxes are the fatty acids with the long chain alcohol. Then we have the triacyl glycerides or the triacyl glycerols, which are made up of the glycerol skeleton, and then this glycerol molecule is attached to 3 fatty acids. Then we have the glycerophospholipids, sphingolipids, glycosphingolipids, and then the steroids. Anyway, we will have this one by one later on, and you will know the structure of each one, because the structure will show how different they are from each other. Okay, so what are fatty acids? Fatty acids are merely carboxylic acids with long hydrocarbon chains. Remember the carboxylic acid? The general formula, it is R C double bond O, and then we have another O attached to hydrogen. Okay, so this R here is the long chain hydrocarbon chain. So the hydrocarbon chain the length of the hydrocarbon chain may vary from 10 to 30 carbons. Most usual is 12 to 18. So the nonpolar hydrocarbon alkene chain is an important counterbalance to the polar acid functional groups. So this one is polar, while this part here is non-polar. So in acids with only a few carbons, the acid functional group dominates and gives the whole molecule a polar character. Like for example, you have acetic acid or the ethanoic acid, CH3COOH. I'll just draw it like this. Basta kay balumo nga ing ani iyahang porma. Okay, so this is just a very small molecule, no? Very small molecule with two carbons. So this, even though this has the hydrocarbon chain, pero gamay bitaw siya, isa lang ka carbon. So ma-overpower jud sa COOH ang ang CH3, ma-dominate siya. So that's why this CH3COOH or the vinegar or the ethanoic acid is a polar molecule. Kaya ang atong suka ug tubig pwede siyang they are miscible. Okay? Kay ang COOH will dissolve or will attract to the H2O or H2O sa tubig or the oxygen sa tubig. However, in fatty acids, the nonpolar hydrocarbon chain gives the molecule a nonpolar character. Okay? So fatty acids are the okay, so mao ni siya ang fatty acid structure. Okay, so you have the long chain hydrocarbon. Okay, this is just another representation, and this one also. And then this is the hydrocarbon chain, which is nonpolar. And then the carboxyl group, do you see this charge? Oh, kaya siya polar. Okay. Okay, so fatty acids can be saturated or unsaturated. We will discuss that later in more details in the next few slides. Okay, now let's go to the fatty acid formulas. Okay, so the formulas of fatty acids are written as condensed formula. So we remember how we write the condensed formula in organic chemistry. So a condensed formula of a molecule is the formula where the symbols of atoms are listed in order as they appear in the molecule's structure with bond dashes omitted or limited. Okay, so while the vertical bonds are always omitted, sometimes horizontal bonds are included to indicate polyatomic groups. Parentheses in a condensed formula indicate the polyatomic group is attached to the central atom to the right of the parentheses. So we have here the first formula. So this is a condensed formula. You have here the CH3. Okay, and then CH2, 6. So the methylene group is enclosed in a parenthesis. Kay taas naman kaayo siya, so pwede raman siya i-condense. Kanin mo ni ang CH26. Okay, so it is the methylene group is placed in a parenthesis, and then you have the COOH. Okay, so remember that? Okay, now another way of writing the formula of fatty acid is the bond line structure, or the line bond formula, or the skeletal structure or skeletal formula. So this line bond formula is a representation of molecular structure in which covalent bonds are represented with one line for each level of bond order. So this line here, okay, represents two carbons joined together. Okay, and then we have another line joined together. Okay, so meaning sa kada tumoy sa line is carbon. Okay, now you can add the correct number of hydrogens. So in this case, sa first carbon, of course, pila ka buok. How many hydrogens are attached to this? There are tulo ka buok, because we know that carbon always has 4 bonds. Okay? Okay, so you have 1, 2, 3, 4 bonds. Now, how about the second carbon, this one? Okay, how many hydrogens will be placed? Of course, naa na may duha, Okay, this one, let's have another color. Okay, kanisha, and this one, so pila na lay kulang to make it 4. Of course, duha na lang ka hydrogen. Okay, okay. So, kanishang second carbon, at to this one represents the CH2, CH2, and CH2, CH2, the methylene group. Okay. By the way, in the condensed formula, you can have this horizontal line or pwede nang diretso na CH2, CH2 without the vertical line. There are two types of fatty acids. One is the saturated fatty acid. You have already heard of the word saturated. The word saturated hydrocarbons when you had your organic chemistry. So to review, when we say saturated, this is a molecule having a single carbon bond. So it indicates that the maximum possible number of hydrogen atoms are bonded to each carbon in a molecule. So when we say saturated fat, it is a type of fat in which the fatty acid chains have all or predominantly single bonds. Therefore, they have no double bond. Now, the simplest fatty acids are unbranched, linear chains of CH2 groups linked by carbon-carbon single bonds with one terminal carboxylic acid group. Okay, so here we have a straight chain, an aliphatic hydrocarbon chain. So all are single carbon bonds. Okay, and then at the end of the molecule of the fatty acid is the COOH or the carboxyl group. So remember, a saturated fatty acid has a long chain carbon to carbon bond. All are single carbon-carbon bonds, and at the end of the chain is a carboxylic group. Okay, so we have here some photos of sources of saturated fatty acid, like butter, cheese, pork, and so on. The list is so long, actually. Okay, so saturated fatty acids have molecules that fit close in a regular pattern. We will show that later. It has strong attractions between fatty acid chains, and they have high melting points because the attraction between the chain is strong. So they have high melting points that make them solids at room temperature. So at 30 degrees Celsius, they exist as solid, just like butter. Here we have a table of common saturated fatty acids, or we can just say SFAs. So many SFAs have a trivial or common name, as well as a chemically descriptive systematic name that is on the second column. Now, the systematic names are based on the number of carbons, the number of carbon atoms beginning with the COOH. That's how we name the carboxylic acid, right? So we also have on the third column the formulas of the SFAs, and then the fourth column will give us the number of carbons, and then the number of double bonds, and then you have the sources, and on the last column the melting point. So let's start with the capric acid. So that's the common name. Now the systematic name is decanoic because if you try to look at the formula, this decanoic acid has 10 carbons. So the prefix for 10 for 10 carbons is deca. Now, since this is a fatty acid, carboxylic acid, so the suffix is oic acid. So that's why the capric acid has the name decanoic acid. And then the fourth column, you have 10 is to 0, meaning there are 10 carbons and no double bond. Of course, obviously, this is a saturated fatty acid. Now, capric acid, the sources are coconut oil, palm kernel oil, and also there are also capric acid. There is also capric acid in durian, in our favorite food, rather fruit, durian. Okay, then you have the lauric, myristic, and so on. Now, let's have the melting point of these saturated fatty acids. If you notice, as the number of carbon increases, the melting point also increases. No? Napansin ninyo na? Okay, so the melting points for the saturated fatty acids follow the boiling point principle. The melting point principle is as the molecular weight increases or the number of carbon increases, the melting point also increases. Okay, so klaro man kaayo, no? Okay. Okay, the melting point of the saturated fatty acids or SFAs depends on two factors. One is the molar mass of the molecules. So, nagkaubos siya, no? From capric down to behenic. So, nagkadako siya nga molecule. So, of course, the molar mass also increases. Therefore, the greater molar mass results in stronger London dispersion forces between the molecules. So, mas stronger ang iyang intermolecular forces of attraction kay taas man ang iyang hydrocarbon chain. So, kung kay strong man siya, dili siya basta ma-break, ma-overcome ang bond, ang intermolecular forces of attraction. So it needs more energy para mag-melt ang fatty acid. Second reason is that the surface area between the molecules, so kanang mga SFAs have greater surface area between the chains, which results in stronger dispersion forces and a higher melting point. So, nagkadako ang molecule, nagkadako pod ang iyang surface area. So, lisod siya i-melt dayon because it needs higher temperature for the fatty acids to melt. Okay, so earlier we had the saturated fatty acids. Kanina pod, we have this unsaturated fatty acid. So, kung katong saturated fatty acids all have carbon, single bond carbon, these unsaturated fatty acids have one or more double bonds in the fatty acid chain. So, a fat molecule is monounsaturated if it contains one double bond, and polyunsaturated if it contains more than one double bond. So the carbon double bond carbon can give either cis or trans isomers. You remember this in your organic chem? Okay, so for a brief review, a cis configuration means that the two hydrogen atoms adjacent to the double bond stick out on the same side of the chain. So the rigidity of the double bond freezes its conformation, and in the case of cis isomer, it causes the chain to bend and restricts the conformational freedom of the fatty acid. So the more double bonds the chain has in the cis configuration, the less flexibility it has. So when a chain has many cis bonds, it becomes quite curved, bent in its most accessible conformations. Now, kanina mang trans conformation, by contrast, means that the adjacent two hydrogen atoms lie on opposite sides of the chain. So as a result, they do not cause the chain to bend much, and their shape is similar to straight saturated fatty acids. Okay, now let's talk about the properties of unsaturated fatty acids. As we have said, unsaturated fatty acids have kinks in their fatty acid chain. Okay, so you have the arrow there on the figure. Okay, so there's a kink in the chain na ay bend, no? Ma-bend siya. So the double bonds in the unsaturated fatty acid cause kinks or bends in the otherwise regular structure as the carbon chain. So as a consequence, unsaturated fat molecules cannot pack together very well. The kinks in their shape make it more difficult to pack their molecules together in a stable repeating array or crystalline lattice. Hence, they have much higher tendency to be liquids. Unlike sa cisganiha na it looks like a straight chain. So, it's easy for them to be packed. Kaya solid ang saturated fatty acids because they can pack together better and tend to be solid. Okay? Next, we look at the different unsaturated fatty acids, their corresponding formula, the location of the double bonds, the melting point, and the source of the fatty acids. The first two fatty acids are monounsaturated fatty acids. We have palmitoleic acid, which has 16 carbons and one double bond found on carbon 9. So you see the triangle there and a number on the third column. That number 9 is where you find that's the location of the double bond. So the counting starts at the carboxyl group, the C double bond OOH. Then you have, so that's the carbon 1. Then 7, so that makes 8, plus another 1 that makes 9. And you find the double bond on carbon 9. Now for the melting point, we will skip that for now because we will discuss that separately later. Okay, so let's go to the source. So example of food which is rich in palmitoleic acid is the butter. Then we have the oleic acid, which has also a double bond on carbon 9. And the sources of oleic acid are the olives and corn. Then we move on to the polyunsaturated fatty acids. We have the linoleic, which has two double bonds found on carbon 9 and 12. Then we have the linolenic, which has three double bonds on carbon 9, 12, and 15. Then arachidonic, which has four double bonds located at carbon 5, carbon 8, carbon 11, and carbon 14. Okay, now let's look at their melting points. What do you observe? How do you describe the melting points of the monounsaturated fatty acids? How about the polyunsaturated fatty acids? In the earlier slide, I showed you a table of saturated fatty acids and their melting points. And we know that the trend is, as the molar mass of the saturated fatty acid increases, the melting point increases as well. Now, let us compare the melting point of the saturated and unsaturated fatty acids. Note that as a group, the unsaturated fatty acids have lower melting points than the saturated fatty acids. Let's go back to the table and describe and explain the first two monounsaturated fatty acid first. Between palmitoleic and oleic fatty acid, the second one, the oleic acid, has higher melting point than the first one, the palmitoleic acid, 13 and 0 degrees Celsius respectively. Obviously, this is because oleic acid has higher molar mass than the palmitoleic acid. Therefore, it has stronger London dispersion forces than the palmitoleic acid, resulting in higher melting point. Now, let's go to the polyunsaturated fatty acids. Linoleic has a melting point of -9. Linolenic has 17, -17. Then arachidonic has -50 degrees Celsius. The melting point is decreasing as the molar mass is increasing. So baliktad siya, it's the other way around. The reason for this is because the more carbon-carbon double bond, the more carbon-carbon double bonds there are in a fatty acid, the less surface area there is between the molecules. Isn't it that the double bond causes a kink or a bend in a molecule? So the more carbon-carbon double bond there are, carbon-carbon bonds there are, the less surface area there is between the molecules. The weaker the London dispersion forces and the lower the melting point. So when you are asked to explain the difference in melting points and boiling points of, let's say, organic compounds, take careful consideration of their molecular geometries. Again, let's do some quick review of our general chemistry. Do you remember the molecular geometry of carbon? It's tetrahedral, right? So in a tetrahedral molecular geometry, a carbon atom is located at the center with 4 substituents, with 4 hydrogens in the case of methane, that are located at the corners of the tetrahedron. The tetrahedral bond angles on carbon results in a molecular geometry for saturated fatty acids that is relatively linear, although with zigzags. Okay, so this molecular structure allows many fatty acid molecules to be rather closely stacked together, the one on the left side. So it's linear, so it's easy to stack them together. As a result, close intermolecular interactions result in relatively high melting points. On the other hand, you look at your right side, the linoleic acid. The introduction of one or more double bonds in the hydrocarbon chain in unsaturated fatty acids results in one or more bends in the molecule. The geometry of the double bond is almost always a cis configuration in natural fatty acids. These molecules do not stack very well. The intermolecular interactions are much weaker than saturated molecules. As a result, the melting points are much lower for unsaturated fatty acids. Okay, so we mentioned prostaglandins in the previous slide. So prostaglandins were first discovered and isolated from human semen in the 1930s by Ulf von Euler of Sweden. Thinking they had come from the prostate gland, he named them prostaglandins. It has since been determined that they exist and are synthesized in virtually every cell of the body. So prostaglandins are unsaturated carboxylic acids consisting of a 20-carbon skeleton that also contains a 5-member ring. Okay, so you have there prostaglandins. You have, if you want to count the number of carbons, there are 20 of them, and you have also a pentagon, 5-membered ring. Okay, there are also OHs on carbon 11 and 15. And a trans double bond at carbon 13. So prostaglandins are like hormones in that they act as chemical messengers, but they do not move to other sites but work right within the cells where they are synthesized. So we know that prostaglandins are biochemically synthesized from the fatty acid arachidonic acid. Okay, so prostaglandins are a group of lipids produced by injured tissues. So they are made at sites of tissue damage or infection that are involved in dealing with injury and illness. They are involved in pain. So if you get hurt from a hammer or naapil ang martilyo ang imong kamot, or you are in the induction of labor kanang mga naknang na tinadyong sakita, or you have fever and inflammation, then in those events prostaglandins are involved. So when you see that prostaglandins induce inflammation, pain, and fever, what comes to one's mind is but aspirin. Do you know what aspirin is? Okay, just a little bit of history. When I was still a child, whenever I got sick, I had fever, my mother would give me aspirin Brand name is Aspilets. Its generic name is acetyl salicylic acid. Mefenamic acid and paracetamol were not yet that common that time. So aspirin or acetyl salicylic acid, mefenamic acid, and paracetamol are all analgesics or pain reliever. But aspirin is also given to patients who have heart disease. Taking aspirin helps prevent blood clots from forming in the arteries and may help lower the risk for a stroke or heart attack. Aspirin is also thought to inhibit the prostaglandin synthesis involved with unwanted blood clotting in coronary heart disease. At the same time, an injury while taking aspirin may cause more extensive bleeding. Okay, so let's go back. So what does aspirin do when one feels pain? So when one feels pain and takes aspirin, the aspirin will block the enzyme called cyclooxygenase or COX-1 and COX-2, which is involved with the ring closure and addition of oxygen to arachidonic acid. Okay, so you see here, this part here for arachidonic, it's not closed. But when you feel pain and then the synthesis of prostaglandin is induced, there is a closure. No, there is a closure of this part here, and then of course there is the addition of oxygen to arachidonic acid, converting to prostaglandins. So the acetyl group on aspirin is hydrolyzed and then bonded to the alcohol group of serine as an ester. So this has the effect of blocking the channel in the enzyme, and arachidonic cannot enter the active site of the enzyme. Now, by inhibiting or blocking this enzyme, the synthesis of prostaglandins is blocked. So mawala ang sakit, which in turn relieves some of the effects of pain and fever. All fatty acids that bear the omega label are unsaturated, containing one or more double bonds. Omega fatty acids are classified according to the location of the first double bond by counting carbon atoms beginning with the last carbon. Okay, so our last carbon here is actually this one. No? Because if you remember our organic chemistry, when we name the carboxylic acid, we start with the functional group. Okay, so this one, carbon 1. But in omega 6, locating the double bond in omega fatty acids, we start from the end. Okay, so omega fatty acids are a family of polyunsaturated fatty acids, meaning it has more than one double bonds that have in common a final carbon-carbon double bond in the N6 position, that is the sixth bond, counting from the methyl end. So you have 1 here, and then plus 4 is 5. So we have the first double bond on carbon 6. Okay, whereas an omega-3 fatty acid is a fatty acid with multiple bonds, where the first double bond is between the third and fourth carbon atoms from the end of the carbon atom chain. Okay, so we have 1, 2, 3. Okay, so the double bond is between carbons 3 and 4. But actually, of course, this is carbon 3. Okay, that's why it's called omega-3 fatty acid. Okay, so these are the sources on your right, are the sources of omega-6 and omega-3 fatty acids. Okay, so we've been mentioning omega-6 and omega-3 fatty acids in the previous slides. So I guess you know, some of you know these fatty acids, their health benefits. No? So what I want you to do is to know all the omega-3 and omega-6 fatty acids and the uses of each, no? So kamo na ang mo basa, okay? So dietitians know there are several omegas found in foods and supplements, but it's important to know exactly what they are, what role they play in the body, how they contribute to health, and what foods contain them so the registered dietitians can counsel patients more effectively. Waxes are esters of saturated fatty acids and long-chain alcohols. So they are nonpolar. So we have here, uh, these are saturated. So all of these are single bonds. And then this one comes, since it's an ester, this one comes from the carboxylic acid, and this part comes from the OH. So this is an ester because you have here the R group, and then you have the carboxylic group, the C double bond OO, and another R. If you can recall, we have the functional group of ester as R, C double bond O, O, and R. Okay, so we have here the different types of, or examples of waxes. You have the beeswax, carnauba wax, jojoba wax. So all of these are they share common uses. They are used as candles, for cosmetics, polish, and so on. Okay, so that's why our fruits. If you notice our apple, if you drop water in it, the water just drips from the outer coating. That is because our apple is covered with wax. Okay, so fats and oils are also called triacylglycerols or triglycerols. They are esters of glycerol and are produced by esterification. Remember the functional group or the general formula of ester? You have the RC double bond OOR. So fats and oils are formed when the hydroxyl groups of glycerol react with the carboxyl groups of fatty acid. So, esterification is the process of combining an organic acid or the carboxyl group of the fatty acids with an alcohol or the glycerol to form an ester. OOR. Okay, on this slide, let's study about the formation of a triacylglycerol. And in everyday language, these are called fats, which is often kind of a feared word, but as we'll see, it's essential for life. Fats in a liquid form is sometimes referred to as oils and is a more technical term for triglycerides. Triglyceride is the word that you might hear when you go to the doctor's clinic. As mentioned earlier, it is also called referred to as tags or triacylglycerols. So triglycerides are literally fats. If you get your cholesterol checked, you will probably get a report on triglycerides, which is really a measure of the fat concentration in your blood. Okay, so here I have the constituent molecules of a triglycerides. The molecule on the left is glycerol. We can see we have 3 carbon chain right over here. Okay, so 3 carbon chains. Okay, each of those carbons is attached to a hydroxyl group or an OH group. If you just get attached to one of them, this makes an alcohol. So you remember your organic chemistry, ROH refers to alcohol. So this is sometimes called, triglycerol is sometimes called a triol. It has 3 hydroxyl groups right over here. Okay, the one in box. And this is considered to be a sugar alcohol. We see why it's an alcohol. It's got its hydroxyl groups and it is also sweet. If you were to drink a solution of glycerol, it actually tastes sweet. A triglyceride is formed when a glycerol molecule reacts with 3 fatty acid molecules. So these in the middle are the fatty acid molecules. Now, why do we call them fatty? And in particularly, why do we call them a fatty acid? Well, you have one part that has these big carbon chains here. Okay, they can actually have different number of carbons. They can have 20s or more carbons. In most biological systems, you tend to have an even number of carbons, and in most animal biology, you tend to have 16 to 20 carbons. So you have this carbon chain here, okay, this one. That part is hydrophobic, meaning it won't dissolve well in water. And that's why people tend to refer to it as a kind of fatty. And over here is the carboxyl group. Okay, and this is acidic. It is very easy for it to donate a hydrogen, because if it donates a hydrogen or a hydrogen proton, I should say, because if this oxygen, okay, this one, or this one, or this one, okay, if this takes those electrons, let me draw the bond between the OH, okay, and then you have the C double bond over there. Okay, so if this hydrogen goes away, since this is a very good living group, it does not take its this bonding electrons with itself. Okay, so it leaves this bonding electrons is left with oxygen, because oxygen, as you know, if you still remember, is very electronegative. So it draws electrons towards itself. So that negative charge can be spread. Okay, so the negative charge here can be spread. Okay, I cannot draw it very well. Anyway, the negative charge can be spread between the two oxygens, between this oxygen and this oxygen. And so it's very willing to give away a hydrogen. So that makes it acidic. So that's where the word acid comes from. That's a fatty acid. And when you have these three molecules, they don't have these three molecules, these fatty acid molecules. They don't have to be. From among the fatty acids, let me discuss with you olive oil. Olive oil is composed mainly of triacylglycerols, or triglycerides or fats, and contains small quantities of free fatty acids, glycerol, phosphatides, pigments, flavor compounds, sterols, and microscopic bits of olive. So olive oil is not a compound but a mixture of different substances. So it consists mainly of up to 83% of oleic acid. Remember, oleic acid is a monosaturated fatty acid with 18 carbons and with a double bond at C9. So it is an omega-9 fatty acid. Olive oil also consists of smaller amounts of other fatty acids, including linoleic acid up to 21% and palmitic acid up to 20%. 20%. So extra virgin olive oil is required to have no more than 0.8% free acidity and is considered to have a favorable flavor characteristics. Olive oil is produced by pressing the whole fruit of olives right here. Okay, so these are the fruit, Olea europea, and then extracting the oil. Olive oil is the main fat source used within the Mediterranean countries, but is now becoming more popular throughout Europe, the USA, Japan, and Australia. But here in the Philippines, we prefer or maybe because of the price, no. So we use coconut oil, palm oil, sometimes canola oil. What else? Corn oil. Okay, so as I've said, olive oil is a bit expensive, you know. So olive oil has been recognized for centuries for its nutritional properties and considered as the elixir of youth and health by antique Greeks. So olive oil is commonly used in cooking, for frying foods, or as salad dressing. It shows a remarkable resistance during domestic deep frying of potatoes or in other uses at frying temperatures due to its lows and saturation. So it is therefore recommended not only as a salad oil but also for cooking and frying. Olive oil resistance to the development of rancidity is combined with a vast array of flavors and color use and distinct features due to differences in cultivars of olives, from which the oil is extracted. So again, in our kitchen, we use the our oil, cooking oil, several times until it becomes black, which is not healthy at all, because you know the double bonds are broken and it becomes saturated. Okay, so it is not good, it is not healthy for our body. Olive oil is also used in cosmetics. That's why our lip balm, it has oil. Some of it is olive oil. It depends, no? It depends on the brand. It is also used in pharmaceutical soaps, fuel for traditional oil lamps, and additional uses in some religions. So it has been accepted uh, that olive oil, particularly virgin olive oil, plays a crucial role in the cardioprotective effect and attributed to its beneficial effects on many cardiovascular risk factors, including lipid profiles, inflammation, endothelial function, blood pressure, insulin resistance, or weight control. So if one is not in a good state of health, then these patients are advised to use olive oil instead of the other cooking oils, which are mostly in our grocery, saturated. This slide discusses the melting points of fats and oils. Both butter and olive oils are types of lipids, but they exist in different phases at room temperature. Lipids that are solid at room temperature are called fats, and those that are liquid at room temperature are called oils. So, how does molecular composition of these substances determine their melting points, and why do they have different melting points? Are the questions that will be explored in this slide. The melting points of fats and oils are obviously different from each other. This can be explained by their degree of saturation and unsaturation. Again, recall that when we say saturation, the substance does have all single bonds, while unsaturation means the presence of one or more double bonds. I also hope that you still remember the intermolecular forces of attraction, the van der Waals or the London dispersion forces, dipole-dipole, and hydrogen bonding. Oils, which are liquids at room temperature, contain more carbon-carbon double bonds than fats, which are solid at room temperature. The lower melting point of oils is related to the higher degree of unsaturation. The presence of carbon-to-carbon double bonds in the oil molecules distorts the long fatty acid chains and the molecule's shape. As a result, the molecules cannot pack closely together. Okay, so remember, when there is a double bond, the chain will bend. There will be kinks that makes it bend. Okay, so therefore, kay naaman siya'y bend na naaman siya'y kink, so it cannot closely pack together. Now, fat molecules do not have the same degree of distortion and can pack closely together. This increases their melting point. Okay, so this one on the bottom. Okay, so these are the fatty acids. So wala siya bend, wala siya na pilo. So it's easier for them, dili siya ma-distort. So it's easier for them to closely pack together. That's why they exist as solid. Now, the poorer packing in oils makes the London dispersion forces between the oil molecules weaker than between fat molecules. So, kay weak man ang dispersion forces sa oils, so less heat energy is needed to separate oil molecules. So, oils have lower melting points than fats. Now, to increase the melting point of an oil, addition reaction between the double bonds and hydrogen can take place. This reduces unsaturation and causes hardening. We will discuss this later. Okay, so we already know that oils have more unsaturated fats. They have cis double bonds that cause kinks in the fatty acid chains. So they cannot pack triacylglycerol molecules as close together as in fats. And they have lower melting point than saturated fats, and they exist as liquids at room temperature. So what are the health benefits of eating more unsaturated fats? Okay, so actually our body needs unsaturated or polyunsaturated fats to function properly. So they are considered beneficial fats because they can improve blood cholesterol levels, ease inflammation, stabilize heart rhythms, and play a number of other beneficial roles. So where can we find unsaturated fatty acids? So they are predominantly found in foods from plants such as vegetables, oils, nuts, and seeds. Okay, this graph shows the fatty acid profile of some of the food that we take. Let's start with the beef tallow. So it has a higher melting point. So this is, of course, a solid, no? So beef tallow is purely fat. So it is primarily made up of triglycerides. The fatty acid profile of beef tallow is 50% of the monounsaturated fatty acid, then a little bit close to 50% of the saturated fatty acid, and a small amount of the polyunsaturated fatty acid. So beef tallow is rendered beef fat. So if you notice, when we eat higop taog bulalo and balbakwa, and then kung mabugnawan siya, di ba, na ay kay greasy nga something, substance on top of the sabaw. Okay, so that's the saturated fatty acid, which is not good for health. Okay, so let's go to butter. Butter contains a good amount of saturated fatty acids, okay, which is a type of fat found in foods, including meat and dairy products. In fact, how many? I think that is about 65% of the fat in butter is saturated fat, while monounsaturated fatty acid is 30, more than 30, and polyunsaturated fatty acid is just less than 10% of the total fat content. Okay, now for coconut oil, oh my god, it has more than 90% of the saturated fat, which has higher percentage than the butter, no? So it's not good also, because there's less than 10% of the monosaturated fatty acid, and then there is no polyunsaturated fats in coconut oil. Remember that too much saturated fat in the diet is unhealthy because it raises the LDL, or the low density profile, low density lipoprotein, or the bad cholesterol levels, which increases the risk of heart disease. Now let's go to canola oil, or the olive oil. Okay, kay mahal man ni siya, di ba? Okay, so olive oil, nga bitaw mahal ni siya. So, okay, so it has more than 80% of the monounsaturated fatty acid, and less than 10% of the polyunsaturated fatty acid, and about 10% of the saturated fatty acid. Okay, so that's why it's healthier. Now for canola oil, okay, canola oil is generally considered a healthy oil because it is very low in saturated fats. Almost, okay, so mga less than 5%. Like olive oil, it is high in monounsaturated fatty acids. Fatty acid, but of course, olive oil has more monounsaturated fatty acid than canola oil. But if we compare the content of the the saturated fatty acids, mas gamay ang canola oil. Okay? Now, let's go to cod liver oil. Let's jump to cod liver oil. Okay, so cod liver oil is a dietary supplement derived from the name itself, codfish. Okay, so kailan tag codfish? Okay, so this is codfish. Okay, so this fish, if you extract the oil, the codfish oil contains omega-3 fatty acids, EPA or eicosapentaenoic acid, and DHA or docosahexaenoic fatty acid. So it is a very good source of vitamin A and vitamin D. In Tagalog, they call this isda sa balakaw. I don't know how do we call that in Bisaya. Okay, so we have the chemical properties of triacylglycerols. The chemical reactions of triacylglycerols are similar to those alkenes and esters. In hydrogenation, the double bonds in unsaturated fatty acids react with hydrogen in the presence of a nickel or platinum catalyst. And in hydrolysis, ester bonds are split by water in the presence of acid or a base or an enzyme. We will have this one by one in the next slides. The hydrogenation of oils adds hydrogen or H2 to the carbon atoms of double bonds. It converts double bonds to single bonds. It increases the melting point and produces solids such as margarine and shortening. So hydrogenation is a process that uses hydrogen gas to change a liquid vegetable oil into a hard spread or margarine. So hydrogenation converts double bonds to single bonds, thus increasing the melting point and stabilizing the oil and preventing it from spoilage caused by oxidation. So are you familiar with star margarine? Okay, so di ba sa commercial or sa advertisement, they say that this star margarine is pampatangkad. So it comes from this star margarine comes from a liquid vegetable oil with double bonds, which is healthier actually. Then in the process of hydrogenation, it becomes solid margarine. So wala na double bond, all single bond na ang sa margarine. So all saturated. Okay, so we've learned that fats undergo the process of hydrogenation, or rather, oils are hydrogenated to become fats. So the addition of hydrogen to alkene or unsaturated fatty acids, or those which have double bonds, result in the formation of a saturated alkane or one with no double bond, with all single bonds. A simple hydrogenation reaction is given here. In hydrogenation, hydrogen is added to carbon-carbon double bond. Okay, so this one. So hydrogen is added here. Okay, this one and to this one and also this one. Okay, so this reaction takes place in a high pressure in the presence of nickel catalyst. So the product of the reaction is a saturated fatty acids that has carbon-carbon single bond. So all of this now, after the reaction takes place, all of these now are all single bonds. So if you want to expand the carbons here, you will notice that these carbons are saturated with hydrogens. Now, what are the advantages of hydrogenation? So one is it increases the melting point. And second one, so like for example, ang star margarine, so taas ang iyahang melting point kesa sa oil. Okay? And second one, it increases the rate of oxidation, meaning it would have a longer shelf life, meaning dugay masira ang pagkaon. Okay, now let's have the cis and trans fatty acids. So again, this is very organic chemistry. So unsaturated fatty acids can be cis with bulky groups on the same side of the carbon-carbon double bond. Okay, so we have this carbon-carbon double bond, and then you have the groups here, a very big group. Okay, so these two groups, two alkanes, alkyl groups are on the same side. So that's why we call this cis. Okay, now for trans, the bulky sides, the bulky groups are on the opposite sides of the carbon-carbon double bond. So in this case, you have this bulky group 1, and then on the other, on the below it, on the other side is another bulky group 2. So these bulky groups are on the opposite side, so we call them trans. Now remember, for this hydrogen, they are on the same side of the plane, so this is cis. But if they are on the other side, on the opposite side, just like sa kaning bulky group, then they call that trans. Okay, so what are trans fatty acids or trans fats, and how are they formed? Trans fatty acids are formed during hydrogenation when cis double bonds are converted to trans double bonds. In the body, trans fatty acids behave like saturated fatty acids. They are estimated to make up 2 to 4% of our total calories and are reported in several studies to raise LDL cholesterol, or the low density lipoproteins, and lower HDL cholesterol, or the high density lipoprotein. LDL is the bad cholesterol and the HDL is the good cholesterol. Now, what are the sources of trans fats? Popcorn, fries, burgers, cookies. I just ate one earlier. Donuts, fried chicken. The most favorite of all the cola and junk foods. So, can we say no to trans fats? It's your decision. Triglycerides, or fats and oils, can be hydrolyzed in the body to produce glycerol and 3 fatty acids in the presence of an acid and heat, or with a suitable lipase enzyme under biological conditions. In a given reaction, which occurs during digestion, we have a triglyceride reacting with 3 molecules of water to form a molecule of glycerol and 3 fatty acids. As you may have noticed, a hydrolysis reaction is an opposite of the condensation reaction, in which a molecule of glycerol reacts with 3 fatty acids to form triglyceride and 3 molecules of water. Now we look at alkaline hydrolysis. In this reaction, we have a triglyceride, which is produced by a glycerol backbone. This is it. And 3 molecules of fatty acids. In this case, this is palmitic acid that reacts with sodium hydroxide and by the action of heat to produce a molecule of glycerol and 3 molecules of sodium palmitate, which is also called soap. So alkaline hydrolysis produces the salt of the fatty acids, which are called as soap. This is known as saponification. So soaps are salts of fatty acid. Okay, now let's go to the other type of lipids, the glycerophospholipids. So in the middle of the name, you have the phospho. So this comes from the phosphorus, and this refers to the phosphorus down here in the form of phosphate. This refers to this is very similar. For glycerophospholipids is very similar to the lipids that we referred to before with the glycerol and 3 fatty acids. But in glycerophospholipids, we have phosphate and amino alcohol instead, and only 2 fatty acids. Glycerophospholipids are polar because of the positive charge of the amino group. Okay, so why is nitrogen positive here? Okay, so remember, nitrogen is stable. It does not have charge if it has three bonding electrons or three bonds and one lone pair. Okay, this one, lone pair. Let me have another color. Okay, three lone pair. So in this case, nitrogen has eight electrons surrounding it. Okay, now for this one, you have no lone pairs at all. Okay? Kaya nga no, gigamit ang lone pair, kani siya, this one is used to bond another hydrogen. Okay? Kaya, this becomes positive. Okay? So, this is ammonia. Okay? So, since this is polar, this glycerophospholipid is a polar molecule, so this means that it can interact with water. Okay, with two lone pairs. Okay, oxygen is partially negative, while hydrogen is partially positive. So this one, since this is positive, it will interact with the negatively charged oxygen. Therefore, this one can dissolve, or glycerophospholipid dissolves in water. Okay, so this is the structure of a glycerophospholipid. So you have the nonpolar tail. This one, you have a long chain, a long hydrocarbon chain, and this is attached to a glycerol. Okay, with the backbone, glycerol backbone, and one of the carbons here is attached to the phosphate group and an amino group. So this part here, since this is amino group is positive, so this is polar, and okay, this is water, so this can interact with this part can interact with the water. This one, of course, since this is non-polar, long chain pa jud, so this will not dissolve in water. Okay, we have a couple of examples of some of the glycerophospholipids. So we have some fatty acids here, and this area is non-polar. Okay, so non-polar because of the long chain hydrocarbons. So it won't interact with water. However, because of this positive charge here, okay, now let's go to the third type of phospholipids, the sphingolipids. So sphingolipids are similar to phospholipids. They are a class of lipids containing a backbone of sphingoid, or they contain sphingosine, which is a long chain amino acid or amino alcohol, a fatty acid, phosphate, and a small amino alcohol. Okay, so they are composed of a polar head group and two non-polar tails. Okay, so how does sphingolipid differ from glycerophospholipid? Okay, so sphingosine is the backbone of a sphingolipid. So it is a long chain unsaturated amino acid, amino alcohol. So it has the name 2-amino because you have the amino group on the second carbon, and 4-trans octadecene 1,3-diol. It is an 18-carbon amino alcohol with an unsaturated hydrocarbon chain. You can see the double bond, which forms a primary part of the sphingolipid. An example of sphingosine is sphingomyelin. So the formula that is given is sphingomyelin. So there is an amide bond between a fatty acid and sphingosine. So there is this amide bond between the sphingosine, the one highlighted in blue, and a fatty acid. Okay, so sphingomyelin is one of the few membrane phospholipids not synthesized from glycerol because the backbone is sphingosine. Okay, so the sphingosine and fatty acid can collectively be categorized as a ceramide. Ceramide. Okay. Then we have the glycosphingolipids. This contains monosaccharides bonded to OH of sphingosine by a glycosidic bond. Okay, so an example of glycosphingolipid is cerebroside. Okay, so again, you have the backbone, sphingosine, and then you have one fatty acid and a monosaccharide. Glycosphingolipids are sphingolipids that contain monosaccharides. So this is a monosaccharide. In this case, this is galactose. Sphingolipids can be a cerebroside with galactose. So the name of this formula is galactocerebroside, which is a glycosphingolipid. Then we have gangliosides, which are similar to cerebrosides but contain two or more saccharides. So cerebroside has only one monosaccharide, but this ganglioside may have more than one monosaccharide. So this is also important in the cell membrane of the neurons and acts as a receptor for hormones and viruses and can accumulate and cause genetic diseases. One of the genetic diseases that is associated with ganglioside is Tay-Sachs disease. Okay, so what I want you to do is to research what is this Tay-Sachs ganglioside. Okay, so these are the lipid diseases. So you have the deficiency of an enzyme that causes the accumulation of glycolipids. So for example, the Fabry's disease, you have the stored lipid galactose glucoceramide, and this is a type ganglioside, and the enzyme absent here that causes the Fabry's disease is a galactosidase. Gaucher's, which is where the enzyme beta glucosidase is absent, and this causes the disease. Sphingomyelinase is absent, is an enzyme absent that causes Niemann-Pick, and the hexoamidase A, the enzyme which is absent that causes Tay-Sachs disease. So I want you to research more of these diseases. Okay, so we have been mentioning about cholesterol, no? In the earlier slides. So cholesterol has the steroid nucleus, which I already showed to you. So this is a steroid nucleus, which consists of 3 cyclohexane rings and 1 cyclopentane ring. There is no fatty acid here, but still this is considered as a lipid. Okay, then we have the cholesterol. This is the most abundant steroid in the body. It has methyl groups. Okay, this is the CH3, an alkyl chain, and an OH. Oh, it's not here, but the OH is in this carbon attached to the steroid nucleus. So this is the structure of cholesterol. Okay, cholesterol is found in meats, milk, and eggs. It is synthesized in the liver and is needed for cell membranes, brain and nerve tissue, steroid hormones, and vitamin D. So our body actually needs some cholesterol to make these substances, no? So our body makes all the cholesterol it needs. But we eat a lot of food that is rich in cholesterol, so of course, mag-accumulate siya. So if one has too much cholesterol in the blood, it can combine with other substances in the blood to form plaque. So you have here a normal coronary artery. The diameter is quite big. It's very clean with no plaque at all. But if you have high cholesterol, it can injure the wall of the artery. So what happens? you have a lot of cholesterol, no? And the diameter of the artery decreases. It's getting smaller. And then if the plaque accumulates, there is the narrowing of artery, which results in the difficulty of the flow of the blood. Okay, so this table shows the amount of cholesterol for a specific serving. So for liver ng baka, 3-ounce serving has 370 milligrams of cholesterol. One egg, the egg yolk only, no? Kaya ang puti is more of protein. So it has 250 milligrams. Lobster, fried chicken, hamburger, chicken with no skin, because ang skin has more of the cholesterol. It has 75 milligrams of cholesterol. So how much more if there is the skin? Then fish, salmon, butter, whole milk, skim milk, 5. And then margarine has 0 because, of course, margarine comes from plant sources. Okay, so it comes from the vegetable oil, so wala joy cholesterol. So, cholesterol is considered elevated if plasma cholesterol exceeds 200 milligrams per deciliter. So, if you have high cholesterol levels, this can, again, clog the arteries that comes from the process known as atherosclerosis, or the hardening of the arteries. But if you have right level of cholesterol, you have a low risk of problems caused by clogged arteries, and that includes heart attacks and strokes. Bile salts. This is the structure of glycocholic acid, which is the bile acid. There are two parts in this molecule. You have the glycine part, or which is the amino acid, the one in your right, in the red circle, that is glycine, and this part is hydrophilic, meaning mo attract siya sa tubig. Now, this is hydrophilic because of the presence, of course, of the COOH and, of course, the nitrogen. Then another portion of this molecule is the hydrophobic portion, or the nonpolar region, the cholic acid. So if you can see, this is a steroid nucleus, and this is cyclic, no? So meaning kay cyclic man siya, ring man siya, this is full of this is saturated with carbon-hydrogen bond, kaya hydrophobic siya. So this molecule is glycocholic acid, which is an amphipathic molecule. When we say amphipathic, that is a molecule that has both the hydrophilic and the hydrophobic parts. Now, what are these bile salts? Bile salts are the primary components of bile. So bile is the greenish yellow fluid made by the liver, and the bile salts are stored in our gallbladder between meals. So ang gallbladder, okay, so this is the gallbladder, the green one. This is a muscular membranous sac that, of course, that concentrates bile. So diha i-store ang bile nga gikan sa liver. Now, this gallbladder is situated beneath the liver. Okay, so you can see the pear shape. And this is just a small organ that has a capacity of 50 ml. So after we eat, and then kaon taog pork, kaon taog beef, no, butter, and so on. So of course, these fats are present in our digestive tract. So what happens is our hormones will send signal to our gallbladders to release bile. So the bile is released into the first part of our small intestine called the duodenum. This is where most of the digestion happens, dito ma-process and ma-digest ang fats. So mura siya, bile salts act as biologic detergents or surfactants that enable the body to excrete fats like cholesterol and potentially toxic compounds such as bilirubin and drug metabolites. So, ang function jud sa bile is to solubilize ingested fats and mo-absorb pud ni sila sa fat-soluble vitamins like the vitamin A, D, E, C. Now, another primary function of bile is to remove toxins, no? Mato kung giingon ganiha, release nila ang mga drug metabolites. So, toxins are secreted into the bile and eliminated in feces. So, kung walay bile salts, there will be build-up of toxins in our bodies. Again, in the absence of bile, fats become indigestible and are instead excreted in feces, a condition called statiuria, or let me spell it out for you. Statiorrhey, rather. Okay, so feces lack their characteristic brown color and instead are white or gray and greasy kung walay bile salts. Now, steatorrhea can lead to deficiencies in essentially fatty acids and fat-soluble vitamins. In addition, past the small intestine, which is normally responsible for absorbing fat from food, the GIT or the gastrointestinal tract and gut flora are not adapted to processing fats, leading to problems in the large intestine. So, ang cholesterol that is contained in the bile will occasionally excrete into lumps in the gallbladder. Mao nang ma-form og gallstones. So, cholesterol gallstones are generally treated through surgical removal of the gallbladder. So, kung wala na kay gallbladder, wala na'y ma-sekretan, wala na'y ma-storan ang bile nga gikan sa liver. However, they can sometimes be dissolved by increasing the concentration of certain naturally occurring bile acids such as chenodeoxycholic acid. So, kung empty imong stomach kay sige ka og vomit, no? So, on an empty stomach after repeated vomiting, for example, a person's vomit may be, ang say color, pag sige na jud halos mulabas na jud imong tinae. So, di ba, ang color sa ato ang suka is maybe green or dark yellow. And unsa ang taste? Di ba? Very bitter. So, the bitter and greenish component may be the bile or normal digestive juices originating in the stomach. So, bile may be forced into the stomach secondary to the weakened valve or pylorus. The presence of certain drugs, including alcohol or powerful muscle contractions and duodenal spasms. Ginatawag ni siya as biliary reflux. Okay, so let's have lipoproteins. Lipoproteins are a combination of proteins and various types of fats. Kaya lipo, fats, and proteins. So these lipoproteins are complex particles that have a central hydrophobic core, kani siya. And then this one is nonpolar. Okay, nonpolar lipids, primarily cholesterol esters and the tags. Okay, so this hydrophobic core is surrounded by, so nakapalibot pod siya by a hydrophilic membrane consisting of phospholipids, free cholesterol, and apolipoprotein. So, polar ni siya. Okay, kaning part. Okay, klaro kayo, you have the OH. So, this is very attractive to water. I'm sorry. Okay, so ang lipoprotein, mura na siya o biochemical assembly whose primary purpose is to transport hydrophobic lipid molecules in water, as in blood plasma or other extracellular fluids. So, halimbawa, ang cholesterol is not soluble in blood. So, para ma-transport siya through the bloodstream, dapat mo attach siya with the lipoproteins. Kaya lipoproteins are the ones that carry cholesterol and the tags through our bloodstream. Okay, now the lipoproteins in the blood plasma are very well studied because they are the mode of transport of cholesterol through the bloodstream and lymphatic fluid. Diba kung magpa-blood chem ang mama or papa ninyo, so makita ninyo sa results na ay lipoproteins. Daghan na siya klase and we will discuss that later. Okay, this is what I said earlier in the previous slides, the slide that there are different types of lipoproteins. Actually, there are 4 major classes of circulating lipoproteins, each with its own characteristic protein and lipid composition. They are the chylomicrons, very low density lipoproteins or the VLDL, low density lipoproteins or the LDL, and the high density lipoproteins or HDL. Maybe some of you have heard already of these lipoproteins, no? Because kung naa kay relatives who have high cholesterol, they go to the lab for blood chemistry. So, nagapa-lipid profile na sila. So, what comes in the result are the VLDL, LDL, and HDL levels in their blood. So, how do they differ? Now, aside from the density, so ang pinaka less dense is the chylomicron, and then the highest or the one with the highest density is the HDL, of course, high density lipoproteins. Now, aside from the density, they also have different composition. Like, for example, ang chylomicron and the VLDL, ang tags ni chylomicron is more than the VLDL. And of course, sa LDL mas gamay and HDL pinakagamay. Now, for phospholipids, pinakagamay ang chylomicron, then going up to HDL, which has the highest level of phospholipid. Then cholesterol, cholesterol esters, and the proteins. So, sa chylomicron, there are only 2% of proteins in the chylomicron. Mas gamay ang kylo kesa sa VLDL, and of course, ang HDL ang pinakataas o percentage of proteins. So, that's their differences, no? So, VLDL has more of the triglycerides than the chylomicron, pero take note that chylomicron and the VLDL or the VLDL and LDL are both considered types of bad cholesterol. While our body needs both cholesterol and the tags to function, having too much of them can cause them to build up in our arteries. So this can increase our risk for heart disease and stroke. Okay, so for this slide, I want you to be the one to explain this diagram. You may prepare a video of yourself explaining this figure, or you make a recording, then submit it in the Google Classroom. Okay, so kamo na pod mo explain ani, and then to be submitted sa ato ang Google Classroom. Steroid hormones belong to a class of chemical compounds named steroids that act as chemical messengers in the cell. All steroid hormones are derived from cholesterol and are synthesized in the mitochondria and smooth endoplasmic reticulum. Then the steroid hormones are transported through the bloodstream to the cells of various target organs where they carry out the regulation of a wide range of physiological functions. See, we are afraid of cholesterol, but actually it is very essential for the normal functioning of our body system. As long as the cholesterol level in the blood is in a normal range, then walay problema. So examples of steroid hormones are the sex hormones such as androgens, like the testosterone in males, and estrogens or estradiol in females. So the testosterone, let's have testosterone first. This is a hormone produced by the human body. So kasagaran, ang men lang ani kay maproduce man ni siya sa testicles in men. Although, ang babae, sa ovary ng babae, they also make testosterone, although in much smaller amounts. So the production of testosterone starts to significantly increase during puberty and begins to go down or it begins to dip after after age 30 or so. So kaning mo change bitaw ang appearance sa man and then sexual development tungod na siya sa testosterone. So testosterone stimulates sperm production also, as well as men's sex drive. It also helps build muscle and bone mass. So kung taas ang testosterone na ay possible health consequences, no? So pwedeng maging aggressive siya and the male would have irritable behavior, mas daghan siya og pimples, unya very oily ang skin, pwede po there will be an increase in muscle mass. Pero kung low level naman ang testosterone niya, the symptoms can include erectile dysfunction and reduced bone mass and sex drive and depression. So, mao nang katong mga low levels, katong mga lalaki nga na low levels of testosterone, naa sila ginakaon nga testosterone boosting foods such as tuna, low-fat milk, egg yolks, mga fortified cereals, and so on. Now, sa babae naman, we call it estradiol. Estradiol is an estrogen steroid hormone, and this is the major sex hormone sa females. It is involved in the regulation of the menstrual female reproductive cycle. Sorry. So estradiol is responsible for the development of female secondary sexual characteristics such as the breasts, widening of the hips, and female associated pattern of fat distribution. Okay. Now, during the menstrual cycle, increased estradiol levels cause the maturation and release of the egg, as well as the thickening of the uterus lining to allow a fertilized egg to implant. So, very important ni siya kung magpabuntis na ang babae, no? So, this hormone is made primarily within the follicles of the ovaries. So, the levels decline as women age and decrease significantly during menopause. So, katong mga menopausal na nasa twilight, hinay na, gamay na, wala na kayo'y estradiol. Okay, so pwede po na ay estradiol sa lalaki pero very naapod ni ma-produce po din siya sa testicles pero very low amount. Also in the adrenal glands, fat, liver, and the breast and the brain. Okay, so it also has important effects in many other tissues including bone, skin, rather, the liver. Okay, so just like sa male, kung daghan og estradiol, magkakaroon pod ng mga pimples, loss of sex drive, constipation, and depression. Kung extremely high naman, they can increase the risk of uterine and breast cancer, as well as cardiovascular diseases. So they also experience women also may experience weight gain and menstrual problem. For men, it can lead to the development of female characteristics and loss of sexual function or muscle tone. So if the body does not have enough estradiol, bone growth and development are slowed, and adults can develop osteoporosis or bone weakness. So girls may experience delayed puberty with low estradiol levels. Napoy mood swings, na naka-connect po na siya, na-link po na siya to low female sex hormone or low levels of estradiol. Now let's go to progesterone. This is also a female sex hormone and is produced mainly in the ovaries following ovulation each month. So kada bulan naga-produce ta og progesterone. Okay? So it's very crucial in the menstrual cycle and also the maintenance of pregnancy. Okay, then we have the uh, no norethindrone. This is a form of progesterone, so synthetic progestin. It is used for birth control or contraception to prevent pregnancy. It is also used to treat menstrual disorders, abnormal vaginal bleeding caused by a hormone imbalance. Okay, let's talk about other steroids, which are the adrenal corticosteroids. These are also called adrenal corticosteroids or simply corticosteroids. Adrenal corticosteroids are natural hormones made by the adrenal glands or adrenal cortex, which are important in maintaining good health. The adrenal glands, also known as suprarenal glands, are endocrine glands that produce a variety of hormones. So they are the ones that produce the hormones, including adrenaline and the steroids, aldosterone, and cortisone. We have two adrenal glands, one in the right and one in the left of the two kidneys. So each gland has an outer cortex or the adrenal cortex, which secretes androgens like the one we discussed earlier, the testosterone. It also secretes mineral corticosteroids such as aldosterone and glucocorticoids. The other adrenal gland is the inner medulla or the adrenal medulla, which produces mostly adrenaline and noradrenaline. Corticosteroids. Okay, corticosteroids include aldosterone, which regulates electrolytes and water balance by the kidneys. So most individuals have never heard about this particular hormone, aldosterone, yet it plays an important role in cardiovascular health. Understanding this hormone will help us understand our body better and help us take measures to ensure optimal health. So, what is the action of aldosterone in our body? Aldosterone affects sodium, potassium, so these are the minerals, no? Total fluids in the body, and of course the blood pressure. So it causes the kidneys to hold on to more sodium, which leads to more water staying in the body. So that's why if we eat a lot of salty food, there is more water that stays in our body. So the more fluid the body holds onto, the higher the blood pressure may become. On the other hand, potassium may decrease as the amount of aldosterone increases. So the action of aldosterone may cause an increase in the amount of sodium in the body or may cause an increase in the amount of potassium released in the urine. So all of these actions are integral to increasing and lowering the blood pressures. Another action of aldosterone is that it directly affects the heart and blood vessels. So if you are struggling while maintaining a healthy blood pressure and also have changes in blood potassium levels, you may want to talk to your doctor about aldosterone. So you consider asking your doctor if your hormones could be the cause of your blood pressure and potassium struggles, especially if lifestyle changes are not helping. So if aldosterone levels are not where they should be, so if aldosterone the level is high or low, talk to your doctor about the changes or treatments that are possible to help your condition. So what happens if one has too much aldosterone? So taas ang level. So the most common cause of high aldosterone levels is excess production, frequently from a small benign adrenal tumor called aldosteronism. So the symptoms include high blood pressure, low blood levels of potassium, and an abnormal increase in blood volume. What happens if gamay pod ang level ng aldosterone? So low aldosterone levels are found in a rare condition called Addison's disease, a condition where the adrenal glands aren't able to produce even the minimum amount of corticosteroid that the body needs. So dili siya ka-produce og corticosteroid. So in Addison's disease, there is a general loss of adrenal function resulting in low blood pressure, lethargy, and an increase in potassium levels. Now, adrenal corticosteroids also include cortisone. Cortisone is a glucocorticoid which increases blood glucose levels and stimulates the synthesis of glycogen in the liver. Hence the name corticoid. Sorry. Cortisone is a steroid drug. No? So it helps decrease swelling and inflammation in your body. It works by stopping the release of molecules that cause inflammation. This also stops your body from having an immune response. So what are the serious side effects? These include allergic reactions. No? The symptoms are skin rashes, itching, hives, swelling of your face, lips, or tongue. Then you also have a fluid and electrolyte problems, muscle problems, stomach problems, and many more. Okay, so we're down to the last slide. Yay! This slide talks about the steroids cortisone, aldosterone, and prednisone. The first two were already discussed in the previous slide, so we will focus our discussion here on prednisone. Who has asthma among you? Who suffers too much itchiness in the body? Maybe some of you are familiar with prednisone, or maybe one of you may have taken this steroid. I am very familiar with this because my children had primary complex when they were still little, and they were prescribed with this steroid. My mother also had psoriasis, which is a skin disease, and this is one of the drugs prescribed to her for itchiness. Now, unlike cortisone and aldosterone, which are naturally produced by the body, prednisone is a synthetic glucocorticoid. This is a medication which has many uses. One is anti-inflammatory. So it prevents the release of substances in the body that cause inflammation. It also suppresses the immune system. So it also acts as immunosuppressant medication, which helps control conditions in which the immune system mistakenly attacks its own tissue. So when one undergoes organ transplant, prednisone is prescribed to prevent the body from rejecting transplanted organs. Another use of prednisone is that it treats many different conditions such as allergic disorders, skin conditions, ulcerative colitis, arthritis, lupus, or breathing disorders. So it is also used to treat high blood calcium due to cancer and adrenal insufficiency along with the other steroids. But this steroids is not to be taken by any patient anytime, no? Although it treats many illnesses, but this drug also carries a risk of serious side effects. Working with your doctor, you can take steps to reduce these side effects so that the benefits of corticosteroid treatment outweigh the risk. Some serious side effects include vision problems, eye pain, redness, or tearing, sore throat, fever, chills, cough, and other signs of infection. This may also cause seizures, depression, loss of contact with reality, confusion, and the list goes on and on. Okay, so we end the lipid. That's all. I hope you understand. Now, if you have questions, then you can post it in our group chat. Bye for now.